Here we're looking at a problem taking an analytical approach to the mean value theorem in contrast to the graphical approach we did with the rulers and finding parallel lines. So the question asks, find the value of c that satisfies the mean value theorem for the following function in the following interval. Now let's take a step back and recall what the mean value theorem says. The mean value theorem says if f is differentiable in an interval from a to b, those are open brackets, typically differentiability is on an open bracket. If f is differentiable on an interval, then at some point c in the interval, the derivative at that point, or f prime of c, is equal to the average rate of change across the entire interval, which may seem like a lot of nonsense at the moment. So let me spell it out more clearly in just a moment. So that's the actual text. What does it actually mean? I'll have to go to a new slide here, but I'll bring the function back in just a moment. It means that the average rate equals the instantaneous rate. The slope of the secant line, which we drew in class, is equal to the slope of the tangent line, which you found by using the ruler on the graphs. And those lines had to be parallel because if two slopes or rates are parallel, their slopes are the same. So what does this actually mean in practice? Well, let's see. The function, once again, was f of x is equal to x cubed minus 2x squared plus 2, and the interval is 0 to 2. Oops. 0 to 2. Well, we can start in a variety of ways, but let's start from a BC, or before calculus, perspective, and simply find the average rate of change. Because you'll notice there are two sides to this equation. Let me choose a different color for this. The average rate and the instantaneous rate. Once you have both sides, then it becomes a matter of setting them equal, as we'll see. But the average rate of change, okay, well, all that is simply finding the slope. And slope, of course, is the change in y over the change in x, or the change in output over the change in input. Well, that would simply be f of 2 minus f of 0 over 2 minus 0. Basically, in 8th or 7th grade problem even, just finding the slope between 2 points. Well, they've given us the x values here, so that's pretty easy. The delta x is 2. The delta y, well, we don't have f2 or f0, so we'll have to do a bit of calculation here. So f of 2 is equal to 2 cubed 8 minus 2 times 2 squared 4 plus 2. So 8 minus 8 plus 2 will give you positive 2. So all of that just for f of 2. And f of 0, mercifully, a little bit faster, you plug it in and you get 2. And there's f of 0. Delta y means the difference in y's. 2 minus 2 is 0 over 2. Long story short, the slope is 0. So the average rate of change for this function over the interval 0 to 2 is 0. Okay? Well, we've now completed one half of our equation that is guaranteed by the mean value theorem. The mean value theorem says the average rate, which in this case is 0, it will equal the instantaneous rate at some point in the interval. And the question is, what is that point? Well, let's continue to a new slide. And I'll write what we found so far here. Average rate, 0. Again, over the interval, 0 to 2. Well, to find our instantaneous rate, we need some calculus. We've already found the before calculus fact. Let's find the part that we need calculus for. So, instantaneous rate. Well, that's the very definition of the derivative, isn't it? It's the instantaneous rate of change, or the slope at a point, rather than across 2 points. So f prime of x for this function, which again used to be x cubed minus 2x squared plus 2, you take the derivative, relatively easy application of the power rule, 3x squared minus 4x. So we want this thing to equal the average rate of change, which we know has to be true because of the mean value theorem. And our graphical approach in class showed us that for a differentiable function, this must be true. So 0, which is the average rate of change, is equal to 3x squared minus 4x, which is the instantaneous rate of change. And I want to make that very clear here, because we're not setting it equal to 0. Okay? The fact that this is 0 is a neat consequence of the fact that the interval was 0 to 2. So this is the instant rate, and this is the average rate. Well, once you're here, it becomes once again an algebra problem, no longer a calculus problem. But since these two need to be equal, let me write it more clearly here, simply solve. So factor an x out. You have two solutions, x equals 0 and x equals 4/3. Now you'll notice that your endpoint here of your interval, because recall our function was over the interval 0 to 2, one of our endpoints is 0. And since we're dealing with an instantaneous rate of change, we need to find the derivative at the endpoint. Well, since we don't know the other side of the endpoint, we don't know what comes before 0, likewise we don't know what comes after 2, because we're only concerned with 0 to 2, x equals 0 is not going to be a valid part of the interval we're concerned with. The mean value theorem guarantees a value inside the interval. So 4/3 is our answer. So that means for f prime of 4/3, tried to write pi there by mistake. Let me erase that. For f prime of 4/3, you will get 0. And there's your value of c, guaranteed by the mean value theorem. And we call it c just to differentiate it, no pun intended, I guess, from a and b, which is the endpoints of the interval, and c must lie within that interval. And indeed, 4/3, or 1.33 repeating, is in between 0 and 2. So x is equal to 4/3 is your answer. All right, hope this helped.